In this podcast, we're going to discuss the relationship between, sorry about that, between Kc and Kp. And Kp is the equilibrium constant in terms of pressures, okay, which would be only useful with gas only equations. All right, so here we have a reaction that has only gases, and in terms of K, we have the products over the reactants, okay? And Kp, all we would do is turn the concentrations into partial pressures of the products over the reactants. Now, there is an equation that describes the relationship between Kp and Kc, and it is Kp equals Kc to the times RT to the delta N. Delta N is the number of moles of the products minus the number of moles of reactants. All right, so in this equation, we have 2 moles of products and 3 moles of reactant. So the delta N would be 2 minus 3, which is negative 1. R is 0.0821, and temperature is in Kelvin. All right, so here's an example problem in which you have this equation, and it tells us Kp and tells us the pressure of N2O4 at equilibrium and wants the pressure of NO2 at equilibrium. So we could simply just set up our partial pressure equation for the equilibrium constant. So we'd have the NO2 to the 2, oh, and then that's in terms of pressure, right? Sorry. And then we'd have the reactant. Okay, so these are both in terms of the partial pressures, and we know the K is 0.133, and we're looking for this one, so we'll call it x squared, and then we know the N2O4 is 2.71 atmospheres, so we'd cross multiply, and we would get there, let's see, 0.36043. So we get 0.36043 is equal to x squared, and then we'd square root it. And that would give us x is equal to 0.6 atmospheres. So the partial pressure of the NO2 at equilibrium is 0.6. Okay? All right, now we're given this one, and it tells us the moles of PCl3 and moles of PCl5, and then tells us how many moles we had afterwards, and ask us to determine the equilibrium concentrations. So we're going to require a ice table for this one. Okay, all right, and the PCl5 started at 8.7 times 10 to the negative third. PCl3 started at 0.298, and Cl2 started at 0. So being that we have no Cl2 at all, we would have to see a change in producing some more products. So that's going to give us this, which makes the equilibrium, okay, minus x. And then we get 0.298 plus x. And then over here we have 0 plus x, okay? And we were also told in the initial problem that the equilibrium concentration of the Cl2 was 2 times 10 to the negative third. So there's the value of our x. So that means we can go back and find all of the equilibrium concentration here by adding or subtracting 2 times 10 to the negative third. So here we'll get 0.0067. Here we'll get 0.3. And then there, that's 2 times 10 to the negative third, also known as 0.002. All right, there are all the equilibrium amounts. Okay, now we're going to have to go back And so there's the equilibrium concentrations. Okay, and now it wants us to get the value of K and Kp. Well, these were concentration values because we were in terms of moles in a 1 liter flask. So that was just moles over liters, molarity going on here. So we can find our Kc very easily by just writing the equilibrium constant expression here. All right. All right, and then we can just plug in our values to get Kc. So we get 0.002, and then we get 0.3, and then on the bottom we have 0.0067. Top is equal to 0.0006. Bottom is 0.0067, and that equals a Kc of this. All right, now it also asks us to find Kp. Now Kp is equal to Kc times RT raised to the delta N. So moles of product minus moles of reactants. We'd have 2 moles of product and 1 mole of reactant, so that gives us a delta N of 1. R was 0.0821. The temperature of the reaction was 298. And delta N was 2 minus 1, which was 1. So we get 24.4658 for the RT raised to the delta N. Now we need to multiply that by the Kc, and that gives us 2.19, which is our Kp value. Okay?